Hey guys, how's it going? So today what we're going to do is we're going to try to figure out how to calculate the area under a curve. Okay? So first I want to remind you about how we looked at those little rectangles that got smaller and smaller, right? And about how the rectangles eventually became a pretty decent approximation of the area under a curve, right? So I want to remind you of that equation that we called these little things here, right? We called them delta x, right? And remember that the height of a rectangle, right? If I made a rectangle that looks like that, right? The height of that rectangle would be f at x, right? So that means that what we're going to do is we're going to sum all the rectangles that have f at x times delta x, right? So we're going to sum all the f of x times delta x, and what we eventually get is we get the integral of f of x dx. Okay, so this is the area, and I notice that this has bounds, and we want a numerical answer because we want the area to be a number. So this is actually going to be the integral from a to b of f of x dx. Okay, so that's going to be the area under the curve. Okay, so now let's just try applying it a couple of times. So the area under y equals 3e to the 2x. So you guys should know what these graphs look like. Okay, so that is ugly. So you guys should know that the graph of e to the 2x, well, you should know that the graph of e to the x just looks like this, right? And 3e to the 2x just stretches it a little bit, so we're not really worried about an exact amount. So we're going to look at the area from -1 to 4, right? So the reason why you need to know what it looks like will come up in the next example, all right? So 3e to the 2x looks like that, and that's the area that we're trying to calculate, all right? So that area is going to be very simple. It's just going to be the integral from -1 to 4 of 3e to the 2x dx. What that means is that, remember, the definite integrals means that we're going to integrate 3e to the 2x. So the 3 doesn't do anything. The integral of e to the 2x is e to the 2x, but then we have to divide by 2 plus c, but that plus c is going to go away in the definite integral, right? Remember that from yesterday's lesson? So we have the integral from -1 to 4, which means that this is equal to 3 e to the, remember we plug in the upper bound first, so 2 times 4 over 2 minus, and then we plug in the lower bound, so 3 e to the 2 times -1 over 2. Okay, and we can simplify this just a little bit, and we can say that that's equal to 3 e to the 8 minus e to the -2 over 2. Okay, and you can get a decimal answer for this, but this is completely acceptable. Okay, so that's the area under the curve there. Okay, all right, let's go to a different example. So find the area bound by y equals x cubed from -1 to 1. Okay, so again, let's picture what that looks like. Okay, so there's my x-axis, there's my y-axis. Okay, and this function is going to look like, remember, x cubed just looks like that. Okay, and now we want to go from -1 to 1. So let's say -1 to 1. Okay, and we'll shade in all that area. Okay, all right. So this is the area bound by this curve. Okay, so we'll try again. We'll say that the area is the integral from -1 to 1 of x cubed dx. Okay, now we'll say that that's the integral of x cubed is x to the 4th over 4 starting at -1, ending at 1. So we'll sub in the upper bound, 1 to the 4th over 4. Subtract, sub in the lower bound, -1 to the 4th over 4. Now you should see something weird happening. 1 to the 4th is 1. -1 to the 4th is still 1. So we get the answer of 0. Now you should be asking yourself, what the heck happened? Right? Because you can see that the integral is 0. The definite integral is 0 for sure. But the area, that's not 0. I've shaded in an area, right? Now you can see that the positive area here and what we call the negative area cancel each other out. Okay? Now that's not right because there is an area. So what we have to do is we actually have to split this wherever the function intercepts the x-axis. Okay, so this happens at 0. Okay, so what we have to do is we actually have to find where f of x equals 0. Okay, so what we say is we say let x cubed be 0. So x equals 0 is a break. So now what we have to do is we have to break up our area. Okay, so what we're going to have to do is we're going to calculate the area from -1 to 0 of x cubed dx, and then we're going to have to add the area from 0 to 1, x cubed dx. And since negative area doesn't make sense, the other thing that we're going to have to do is we're going to have to take the absolute value of all of these things, because negative area doesn't make sense, right? Okay, so let's do that. So the integral of x cubed is, as we said before, x to the 4th over 4. We're going to calculate from -1 to 0, and we're going to take the absolute value, and we're also going to do the integral again, x to the 4th over 4 from -1 to 0, and we're also going to take the absolute value. This part's going to be positive, so absolute value is not going to do anything there. So here I plug in 0, I get 0 over 4. I plug in -1 and I get 1 over 4 absolute value, plus, oh sorry, I made a mistake over here. This should actually be going from 0 to 1, right? So it should be going from -1 to 0 and then starting at 0 going to 1, right? Because that's what it says. Okay, so plus, and then I'm going to plug in the upper bound, 1 over 4, subtract, plugging in the lower bound. Okay, so this gives us the absolute value of -4, which is 1 over 4, plus 1 over 4, which is 2 over 4, or 1/2. Okay, so what that means is that the value, that the amount that's actually shaded in here is a 1/2 unit squared. Okay, and that's all. So here's the homework that we're going to be working on in class. Try it out if you have time, otherwise we'll have time in class tomorrow. Alright, see ya.